Hi everyone. All right, so you made it to the last week. So great job. So let's take a look together at what we have coming up here. All right, so let's go to the modules. And we are now on unit 3. All right, so we're looking at, finishing up unit 3 this week. So remember that the assignments for chapter 11 on magnetism and chapter 12 on light are all due on Sunday. All right. And since we're going to be done with unit 3, that means that we have exam 3 coming up next week. You'll see that everything is very similar to what we had in the previous 2 exams. So it will open up on Monday at 9 a.m. It will be available until Friday at midnight or a minute before, and you'll have 35 minutes, 35 multiple choice questions, sorry. You'll have 3 hours. Uh, and it will cover all of the chapters from unit 3. You will have 2 attempts again, and just like before, please make sure to get started with the practice exam before you take the actual test to get an idea of how you're doing with the material before you start. All right, so we talked about that before. And I had mentioned unit 4 quickly, but we're going to be spending more time looking at unit 4 today. So that is the last unit for this course. And you can see that, so thankfully there is no exam 4. So we have to fit everything in 7 weeks during the summer. So that's a little bit tricky. And so we're closing up with the unit on modern physics. So no exam, so there's no exam 4, but you still have some assignments here. So you have 1 homework assignment per chapter and a couple of discussions. So we don't have one for the last one, just to keep things a little bit on the lighter side on these chapters, given that this is the last week. And these are the last chapters. So once again, good job on making it this far. I know it's hard during the summer. It's very intense. And as I've mentioned many times before, we could be spending many weeks on any given one of these chapters. So, if you have any questions later on, please don't hesitate to reach out. Even, once we're done with the course, I'm happy to answer any questions you may have. If you want to learn more about any one of those topics that we have talked about during this course, and there were many. So, all right. So why do we have a unit on modern physics? Why is it called modern physics? So this is essentially a lot of the physics that's been done more recently, right? And so kind of starting, a century ago or so. And it's going to be different from what we've seen with classical mechanics and the previous chapters. And it's going to seem like, we're sort of revisiting some of the things that we've seen and saying like, oh, wait, so this doesn't actually work. So before we start, I just want to say that what we've seen so far works just fine. It's all a matter of context. So what we're going to see here is that we're going to need new tools to explain what's going on when we're pushing some limits. Those limits are going to be, so in the case of quantum mechanics, we're going to start looking at things that are very small, and we're going to see that when we're looking at the very small, we're we're going to start seeing things acting in a very strange way. It's only strange to us because we're not used to that, because we live in a world that can very much be described by all the classical mechanics that we've studied so far, because of the scale and how objects behave around us at the scale that we're seeing. All of those things are very well described that we've seen with the tools that we've studied so far. So what we're going to see is what happens when we go to, we're going to be moving away from those scales and pushing those limits. With special relativity, what we're going to see is that, again, things start looking a little bit or very different when we're studying objects that are moving very fast. And very fast means close to the speed of light. All right. So once again, what we're going to look at now is sort of the more general picture that would describe objects that are moving at any speed. And it turns out what we've described so far was a good approximation for our kind of everyday life. But that those models start breaking when we have objects that start moving too fast. And so we're going to see sort of the broader, more general picture with special relativity, and see what happens to objects that are moving very fast. And in chapter 15, we're looking at applications of all of that. So we're looking at applications in nuclear physics. We'll see that when we study quantum mechanics, we'll be talking a lot about atoms as well. So what you have in the atom, you have a nucleus that's made of protons and neutrons, and that's surrounded by a cloud of electrons. And nuclear physics essentially studies the nucleus. So we very much need to understand, chapter 13 before we get to this one. And this has a lot of applications. Probably the first one that comes to mind would be, nuclear power plants. So this is very important in terms of energy, but also in terms of understanding reactions in the sun, which again are very important to us. But also there's a lot of application of this in medicine. So I know some of you are interested in going into the medical field. And so lots of applications of that there as well. And particle physics goes, it's almost like going one step further in terms of the scale, because the nucleus is again made of neutrons and protons. As it turns out, those are not elementary particles. They're made of other particles. So they're made up of quarks. And it's essentially, particle physics looks at sort of the smallest possible, so elementary particles. So it's interesting to understand exactly, right? If you look at your hand and what it's made of, right? Because you have the molecules that are made up of atoms, and then these atoms have these neutrons and protons within them, and then those are made up of quarks. And how does that work, and how does it stay together? But there's a lot of the modern experiments are looking into this particle physics field. And for example, you may have heard about CERN that's near Geneva in Switzerland. Essentially the idea is to take up some particles and have them collide and look at what happens. And why would we be interested in that? So we're trying to push the limits of our understanding of physics. And in doing so, it's almost like we're traveling back in time and looking at what's going on, we're a little bit after the Big Bang, because we're looking at, having the conditions of, what happened then, so we can understand, our universe a little bit better. In some ways, it relates to that. I just gave you an extra credit assignment. And I'll actually, let's see here. So just a reminder, since I'm on that, we have sorry, I'm not used to this view because this is a student view. And I guess it's this in the, no, this is overdue. It's showing up like this because, so we have this extra credit. Oh, here we go. The GEMS Web Space Telescope extra credit discussion. And that is also, taking a look at the universe the way it looked like 13 billion years ago. So anyways, there's some cool stuff happening in the world of physics and all the time, but this was the latest big news. All right, so just going back to our unit 4 here really quick. So at this point, I think you know pretty much how to navigate this. I'll just click on this, but I may not go through all of the pages to save a little bit of time. All right, so again, the learning outcomes for quantum mechanics. And we're going to look at some of the strange behaviors that we're going to see as we're looking at, small objects like the hydrogen atom. If you found that this chapter is a little bit puzzling because it's going to give you physics that's very different from what we've seen before, well, don't worry, you're not alone. Physicists were very, kind of confused about quantum physics because, it's very much based on probabilities of finding, electrons in a given place instead of, being able to see them. We're used to having a position for a particular object, and it gets a little bit more complicated than that, or a lot more complicated than that. And so a lot of people were actually kind of, in disagreement because it didn't seem like the way the universe should be described, or at least physics. And so they came up with all kinds of, with these paradoxes. And one of them you may have heard about is Schrodinger's cat. So we have this video here for the discussion. And so I would invite you to watch this video, which also, I think what I like about it is that it can also explain why quantum physics is so important in a lot of things that you actually do in your everyday life. So there are applications of this crazy theories that are out there. But if you'd prefer, mentioning another paradox that you know about, please feel free to do so. And if you have a video that would explain, or some explanation, that would be great as well. So you can talk about something else, or you can talk about something that you see on this video. All right, and you may not walk away being an expert on quantum physics. That's normal. But hopefully you'll get to understand why and what it's all about. With special relativity, again, we're looking at moving objects that are moving at speeds that are small fractions of the speed of light. And we'll see that it's going to give us all kinds of interesting effects in how we're going to measure time and length. So that's going to give us some different perspectives. You'll see that I have solved some of the homework questions here. So make sure to check here if you have questions on the homework. So don't worry about these messages here because I said I would not walk through, but I am. It's just easier to navigate. So you have videos here that explain all of this, in addition to those other ones that were on the first page. And the discussion here is also a a commentary on another video. And this one it's pretty cool. So it's a VR video, so it's virtual reality, and I would, if you can, I would actually watch it from your phone, just because you can essentially look around. You can also do it from your computer. You can and you'll be able to see what it is to experience speeds that are close to the speed of light. The reason for that is that in the video, you have Captain Einstein, who's able to actually change the speed of light to something that is much smaller than the 3 times 10 to the 8 meters per second, just to kind of get a feel for what it would look like if you were traveling close to the speed of light. So again, I would advise just, again, trying to do on your phone, but if you're doing it from the computer, you can also, you'll see that you can look around the screen, so you can essentially look, you'll be traveling on a boat, so you can look straight up, and you can also, move to the side and navigate that. All right. And then we have our final chapter. All right. So final chapter with your final homework assignment, chapter 15, all about nuclear and particle physics. So I told you a little bit about that. Lots of, again, applications here of what is in this unit, and a lot of the concept that you see here have important applications in a lot of various fields, and the main ones being how we generate energy and electricity, but also there's many applications of this in medicine. And again, you have some homework solutions here, but otherwise the regular stuff. All right, with the content and the final homework set. All right, so I will stop here for this announcement. Please reach out if you have any questions. And again, so we're in the final week here. You're almost there. So great job, everyone. And let me know if you need anything. All right. Thank you. Bye.